Welcome back, friends. So, we were discussing the Dirac propagator and started doing some simple applications in quantum electrodynamics, and what we are doing essentially is treating it everything in terms of Green's functions methods, and we have tried to do derive the Green's functions propagators for the electron field, meaning or the fermionic field, the Dirac field essentially, and we also initially mentioned about the propagator for the photon field essentially. So, like I said, the quantum electrodynamics is a theory of one electron and one photon. Well, that is the only thing essentially, and then we talked about the epsilon prescription, went about deriving the propagator using this thing essentially, and then we also looked at the corrections to the propagator in the presence of interactions. So, we derived these relations, the Dyson series, and then we also showed that this Dyson series is equivalent to Feynman diagrams essentially in terms of various aspects at higher and higher order in perturbation theory. Now, which is very good, but I wanted to, then we wrote down simple process, simple QED process like E gamma, E Compton scattering, Bhabha scattering, which is E plus A minus going to E plus A minus, molar scattering, pair annihilation and pre-creation. Now, we started doing the calculations for each of these things. So, for Compton scattering and for pair creation and pair annihilation. And other aspects essentially. Okay. Before going further, I wanted to, well, you can do everything in one particular fashion essentially. So, we started doing this calculation Compton scattering. Okay. The method which we learned in terms of Green's functions methods does not really require, I wanted to make one particular comment here, that the method which we learned or the Green's functions method does not really require that the photon field should be dynamic. Okay. You can write it, you can just replace it with a potential and then you get back your solutions exactly in the same fashion as previously essentially. Okay. We will do one example of that today, we will do meaning on the course, but what we are doing, but if you take process with a photon in the external line essentially, like if you take Compton scattering, pair annihilation, pair creation, in all this process the photon field is dynamic. Okay, is dynamic. That means you have to do second quantization and define the photon wave functions essentially. The photon, you cannot use the photon potential essentially, the electromagnetic potential, the static potential, you have to use the photon wave function, which I said I will do it in the next class essentially while we started doing the Compton scattering. Okay. The Compton scattering, okay. So, we will do these diagrams one by one essentially. Today we will go in slightly more detail in the Compton scattering. Before doing that, okay, I want to mention what is the photon field. What is if I take what is the photon field solutions essentially. So, the basic idea here is that you write the Lagrangian for the photon field, which is nothing but L electromagnetic is equal to minus by 4 by 1 F mu nu F mu nu, where F mu nu is equal to del mu A nu minus del nu A mu, okay, which is the antisymmetric field strength tensor of the electromagnetic field. Now, this has a solution, this you know already that this has a solution that A mu is equal to J in the absence of sources. Now if you want to make them into particles, now this you have solutions. You can take the A bar is equal to 0 and A 0 is the axial potential. A mu, if you remember, is nothing but rho, the electromagnetic potential phi or rho, and A bar the vector potential. So this is the static potential, the electromagnetic potential. So you can always choose a gauge, you can always choose a big gauge such that A bar is equal to 0 essentially. Now there is a gauge dependence already. Okay, so it is not unique, there is a gauge dependence. If you remember what is your gauge, gauge essentially remember that gauge is the choice of A bar. A bar is not unique, you can have several, so which gives you the same Maxwell's equations. Okay, you do not have a large variety of choices of A bar are available essentially. What we want at the end of the day is that A mu has solutions in terms of some polarization vector e power I k x essentially of k essentially. Okay, as solutions, as this is the kind of solutions we want essentially, and the process of getting this you can give it, this is the polarization vector and that is the Paine Blaise. Okay. This is the kind of solution what we want essentially. This you can write it in terms of some solution, some wave essentially with the polarization vector corresponding to it. Why we want to, and this polarization vector is an important thing because it tells you how many polarizations a photon can have, and given that the photon is massless, it turns out there are only two polarizations possible which are both transverse to the direction of the momentum. So there are really two polarizations possible which are both transverse to the direction of the momentum, which we know because we know that this is always true, that the photon always has transverse polarizations. There are various theorems which show that essentially. One is coming from special theory of relativity, there is experimental observations, there are various things essentially. So you can show it also for every massless vector in special theory of relativity is only transversely polarized given. Okay. So this comes out automatically from special theory of relativity or representations of particles and so on. So but also the as a special case that as a special as a special case for photon, you can show that the photon you can experimentally know that because it is a massless photon essentially, it is a massless wave, you know its light is always transverse polarized essentially, you know that light is always transverse polarized. Okay. Now given this kind of solutions, this is the kind of solutions you can use it. Now there is a method to give it a particle interpretation. This wave solution can be given a particle interpretation So, under the method of second quantization, we can interpret this entire thing in terms of a wave solution in terms of particles. The okay, and these waves can be written in terms of particle exactly in the same fashion essentially, except that you now determine in terms of this wave solution can be interpreted of a photon of a particular momenta and a particular polarization. Okay. In terms of polarization and momenta, you can write them as particular particles essentially. You can do that with the process of second quantization. Now, in the course of these lectures, I am not sure whether I will be able to cover the entire process of second quantization, but today I will just mention that you can I will just mention qualitative steps just before. If I have time, I will come back to this later on. Second quantization goes as follows. Okay. So, take the solution A mu, essentially A mu wave function. Okay, you take the A mu wave function. Now, you write the Lagrangian for the A mu essentially. A mu, and the second thing is you have to choose a gauge. There are various subtleties involved in the photon second quantization, because some of the gauges, some of the choice of the gauges could lead to unphysical results, not unphysical results, but lead to complicated results. They become when you do higher order calculations essentially, they lead to problems essentially. So, there are various gauge choices you need to choose essentially. There is a Coulomb J, there is a RJ gauge, there is a several choices of the gauges you have. Okay, there is a Landau gauge and so on. So, essentially each and in general in quantum field theory there are something called RJ gauges. So, we will not go into the great details about it because well it comes as one of the things in quantum field theory at later on stage essentially. So, but given this all these choices of choose a gauge essentially, choose a gauge, you choose a gauge for this wave function and then write the Lagrangian in terms of A mu, and you also have del A by del A dot essentially, that also is important. Okay. Now, the point is that A dot has some complications essentially, A dot has some complications because A dot is nothing but K by C essentially, A dot is nothing but K by C. Well, not, let me not use the word complications. Okay. So, if you just choose the pi A mu, which is nothing but del L by del A dot A mu dot. So, write the Lagrangian in this. This is quadratic, this is quadratic in A mu and pi A mu. Express this in terms of simple harmonic mode. Raising and lowering operators a dagger for each mode. For a mode means dependent upon epsilon and k, okay, and a dagger epsilon k. You can express this entire thing. So the A mu will become a function of okay, function of A and A dagger operators, but these are not raising and lowering operators, but they are creation and annihilation operators. Okay, they are creation and annihilation operators. At the qualitative level, if you want to understand it, meaning not in the modern, in slightly different fashion, I think one of the first readings of second quantization of the electromagnetic field can be found in J.J. Sakurai. There is a very nice book by J.J. Sakurai on called Advanced Quantum Mechanics. So, which this okay. Now, what are these particles creating essentially? Where are these particles? So, this is a very nice book to have the first reading of second quantization. Of course, then you can refer to many of the modern literatures like on quantum field theory. Essentially, you can do it and do it. Now, what does they mean? Where are they getting created from and where are they getting annihilated from? They are created from the vacuum. So, the lowest state, because all the harmonic oscillators are essentially, because these raising and lowering operators are like creation and annihilation, they are like harmonic oscillator operators, right, essentially. So, for every mode you have a harmonic oscillator, for every k and epsilon you have a harmonic oscillator like scenario. So, the ground state of the harmonic oscillator has half h cross omega energy states, it is not 0. So, the vacuum is integral so half h cross omega, some over all the states essentially integral over all the k's, okay. Okay. Let me write it in terms of omega, but from omega you can go into k essentially half h cross omega, okay, where omega is equal to 2 pi by k essentially. So, this half k cross omega is integrated over all this thing which is a divergent sum. So, this is the vacuum state which is highly energetic. So, this is highly energetic, but you set the energy to be 0. This is like the Dirac sea, okay. Okay, energy, you set the energy to be 0 because the ground state can be always be chosen to scale in whatever way you want essentially. You can scale the ground state, you can choose the energy of the ground state because you can instead of when which is this goes as infinity, this integral goes to infinity, this integral goes to infinity. Now, you can set this infinity because what you are seeing is only differences, just like Dirac sea, what you are seeing is only differences. Exactly when we discussed Dirac sea, we discussed this thing that what is the energy of the vacuum will not make a difference because what you are saying is the differences between the ground state and the first energy state, second energy state and first energy state and so on. So, what you are seeing only is the differences. So, you can set it to 0, the energy of the vacuum to be set into 0. And when you set the energy of the vacuum to be set into 0 essentially, so then you can create particles, then you can create particles from the vacuum Okay. So, A dagger will give me a state with a particular, we used polarization and energy essentially, with a particular polarization and energy essentially. So, this is what this A dagger is a function of k and omega, k and epsilon. This will, now what does A do? A annihilates the vacuum. A annihilates the vacuum essentially. A is an annihilation operator, it annihilates the vacuum essentially. It does not create a particle, it annihilates essentially, it is an annihilator operator, it annihilates the vacuum. So, from this vacuum you create all this bunch of states essentially, which we call it as the Fock states. So, you can apply several times, a particle with n particle state can be created, n particle state with several photons, because it is a boson, you can create something like AK per K, K and A epsilon, say for example AK one K1 epsilon 1 AKN dagger KN n, everything acting on the vacuum, which gives me a state which contains several photons, which gives me a state, it is a many body state which contains several photons with epsilon 1, epsilon 2, epsilon n, k, so on, so essentially, with values of k and everything essentially. Okay. So, this is the entire idea of second quantization, this is the entire idea of second quantization. Now, this is what makes the field dynamic. Okay. That means instead of taking it into so this is the what I used essentially. Now, these polarizations are also complete, the polarizations are complete, they are orthonormal. So, they form a complete set, they form epsilon epsilon prime should be equivalent to delta 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 k k prime. They are orthonormal states, they form a complete state, these wave functions are completely they form a very well behaved set of things. Now, the process of starting with a wave function and interpreting it in terms of particles is called second quantization. Now, the point is that what you did was you started with a solution and then you put it back, you tried to interpret in terms of why you call it second quantization is you are in the old days it is called quantization of the wave function. And that is the reason why it is called second quantization. This is the old nomenclature, but these days we do not really consider this in particular fashion. What we call it as is quantization of the electromagnetic field, essentially quantization of the field. These days we call it as the quantization of the field. Which we will do in a completely quantum field theory technique essentially. That is the reason why it is called quantum field theory, you are calling it as a quantization of the field. Now, so with this these particles can be, now once you make the field dynamic, then you can interpret the wave functions. The photon can be thought as a wave function of the photon or a particle, then you can treat it really like a particle, because in Compton scattering it is like a particle, right. Essentially the photon behaves like a particle in real, it comes, hits the electron, goes away essentially. Okay. You can think in terms of that. So now we go back to Compton scattering. So Compton scattering, if you treat them as particles because then you are giving a different momenta. And then your okay. Yeah, just to summarize before going to competence scattering again essentially. So, photon field solutions, you start with the wave functions. You start with the solutions of the electromagnetic field equations essentially. So, delta A mu is equal to 0 in term and phi and A mu, and then you express it in terms of plane waves and under polarization vector essentially, under polarization vector. This is the solution what we want essentially. We choose a gauge to arrive at it, and the way we proceed to do it essentially is that of the many choices of the gauges you choose, you see that it is quadratic at A mu and pi A mu. Express this in terms of raising and lowering order operators. In terms of A and A mu or the pi A mu, the conjugate momenta essentially. Now but instead of calling them as raising and lowering operators, because there are several modes possible, because the momentum is not is fixed or okay, you have several kinds of momenta which are allowed, and polarizations, two kinds of polarizations allowed. So you call them as creation and annihilation operators, and you express the solution in terms of these functions, either in terms of an integral or you can write it in terms of discrete sums, but running from infinity essentially, minus infinity to plus infinity essentially, because all the polarizations are allowed, all the momenta are allowed essentially. This will allow you to treat the photon as a particle, interpret the photon as a particle of a particular momenta and a particular polarization. Of course, you can say that it is the same thing as a wave, but that wave particle duality always exists in quantum mechanics. Now when you do that, when you write the spectrum of the harmonic oscillators, you have an infinite set of harmonic oscillators, and the energy of these harmonic oscillator, then you have a number of operators, and then you can derive the Hamiltonian, and you see that the 0 point energy of the infinite number of harmonic oscillators just adds up and forms a vacuum. This is nothing but the 0 point energy of the infinite number of of harmonic oscillators. So this 0 point energy, if you sum it all over for all this infinite number of harmonic oscillators, is infinite. Now you have to set it to 0. There is a proper way of prescription of doing it in field theory essentially, but for our cases we forget about it essentially. We just say that I can set this entire infinity because it does not make sense. Like we will use the philosophy of Dirac-C. Okay. From the case of Dirac-C viewpoint, we know that what we measure is only the differences between energy levels, and the energy of the vacuum will not make any sense, will not make any impact in the final experimental determination. In this way you can set the entire energy of the vacuum to be 0, okay, entire energy and vacuum to, and still call it as a 0 state essentially, because what is the energy of the vacuum will not make any difference, because what we actually measure is the differences between the energy states, the ground state and the first state, second state and third state, and so on. So with this we will notate the vacuum state as a 0 state essentially, and then the creation operators are defined in such a way that acting once on if the A-dagger operator acts once on with a momentum k1, k and epsilon, will produce a photon with a polarization k and a momentum of k and polarization of epsilon essentially. This is what it does essentially. So it is what it does, and the annihilation operator annihilates the vacuum. Of course it can annihilate any other momentum state and destruct a particle essentially. Any other state if you take essentially, it reduces the particle, it annihilates the particle essentially. So this is what these operators do. Where do they act? They act on the vacuum or any end state essentially. These are the creation and annihilation operators, and the Hamiltonian is given in terms of this creation and annihilation operators anyway. So without going further ado, we can just take an example of n particle photon state can be written in terms of n times with different momenta and everything, A operators, A dagger operators acting on the vacuum. So this entire treatment is the thing that makes the photon dynamical and this entire treatment makes the photon dynamical and particle like. With this, now we are ready to do simple calculations in Compton scattering. Okay, I will revise the other process one by one and in the next lecture. So okay, we will continue with the Compton scattering and other simple process, and there are some trace theorems which we will revise and see how this process works. And I will also tell you the method which we solved can be also applied to the case when the photon is not dynamical. That is an important thing, that when the photon is non dynamical, it is also the Green's functions methods also get applied, and these two aspects we will see in the coming lectures essentially. Okay. Thank you very much.